Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we will discuss the expansion theorem in this module from the paper Mathematical Physics. So let us see what we are going to learn in this module. In this module, we will learn to use the results of the last unit on eigenfunction expansion. We will learn about the important Hilbert alternatives. Let the function p of x be the transform of a continuous and bounded function h of x by the kernel k of xy. That is, p of x is obtained by integrating h of y with the weight k x of y. So px is equal to integral a to b kxy hy dy. So px is the transform of hy. If the function can be expanded as, that is kernel, if the kernel can be expanded as kxy is equal to a sum over I from 1 to n fix fiy divided by lambda I, such that the series converges uniformly in each variable, then px can be expanded in the orthogonal basis of eigenfunctions of the kernel kxy. In that case, we can write px equal to sum over I from 1 to infinity pi fix, such that pi is equal to the integral a to b of px multiplied by fix dx. So we have pi is equal to integral from a to b of px fix dx. This has been done by using the orthonormality of the functions fi's. However, equation 11.2 is not proved, and so the equation that px is equal to sum over I from 1 to infinity of pi fix is not established. We will, however, use equation 11.4, that is, pi is equal to integral a to b of px into fix dx as the definition of pi. So we will use this as the definition of pi as substituting the expansion equation 11.1 in equation 11.4. We get pi is equal to an integral over dx and dy from a to b of k, a function of xy, and hy multiplied by fix dx dy, which is equal to 1 upon lambda 1, the integral a to b of hy fiy dy is equal to hi by lambda I, where we have used the property that the kernel is symmetric. Then by Bessel's inequality proved in the last unit, we have integral of summation I is equal to 1 to infinity hi square is less than infinity. Next, the same Bessel's inequality now gives us integral k square xy dy is less than or equal to sum over I is equal to 1 to infinity of the square of the integral of k multiplied by fi, a function of y dy, which is equal to the sum over I from 1 to infinity of fi square by lambda I square. The last sum therefore converges, since the left hand side is bounded uniformly in x. Let n, k, l up to m be a sequence of integers. Then from the last equation and Schwarz inequality, we have hn fn x divided by lambda n plus so on and so forth up to hm fmx divided by lambda m whole square is less than or equal to hn square plus hnl square plus hm square, whole thing multiplied by the sum over I from n to m of fi square x by lambda I square. But summation I is equal to 1 to infinity hi square converges. Hence, if n is large, hn square plus hl square etc. up to hm square is small, and it goes to 0 as n becomes larger and larger. The sum I is equal to n to m for fi square x by lambda square is bounded by an x independent bound. Thus, the term in the left-hand side of the equation goes to 0 as n goes to infinity. The series sum over I is equal to 1 to infinity hi fix by lambda I therefore converges uniformly and also absolutely. Further, from the equation 11.5, we have this sigma I from I is equal to 1 to infinity of pi fix is equal to sigma from I is equal to 1 to infinity of hi fix by lambda I. And hence, from the result following equation 11.7, the above series converges absolutely. What remains to be shown is that the infinite series 11.9 is actually Px, equation 11.3. To prove this, we construct a kernel Kn of xy as k of xy minus the sum over I from 1 to n of the product of functions fi of x into fi of y divided by lambda I. Then p of x minus sum over I of pi fix is equal to the integral from a to b over dy of the function kn and hy because of orthogonality of the fi's. So we multiply this equation by an arbitrary function t of x and integrate. So we have the integral dx tx multiplied by px minus sum from I to n of pi fix, and on the right hand side we have this equal to the integral a to b over dx integral a to b over dy of the kernel kn function of x and y h of y and t of x. We now invoke the theorem proved before in the last unit, which shows that the right hand side of this equation vanishes in the limit n goes to infinity, since tx is completely arbitrary, which means that p of x is equal to the sum from I is equal to 1 to n of pi fix, which establishes the equation 11.3, which we wanted to prove. We thus have the expansion theorem. Every continuous function p of x, which is an integral transform of another function h of x by a symmetric kernel k of x and y, like what we have shown in equation 11.1, then such a continuous function can be expanded in a series in the eigenfunctions of k, which is shown in equation 11.13, and importantly, this infinite series is uniformly convergent. This crucial theorem thus extends the results that we had for degenerate kernels and immediately leads to the solution of the inhomogeneous Fredholm equation, which we will discuss in the next section. We now consider inhomogeneous Fredholm equation f of x is equal to g of x minus lambda integral from a to b the kernel k into fy dy. With the symmetric kernel, we apply the expansion theorem established in the last section to the function g of x minus f of x, which therefore satisfy equation 11.1 as its left-hand side. We can therefore expand g of x minus f of x in terms of the eigenfunctions fix's of the kernel kxy. Gx minus fx sum over I from 1 to infinity fix are the eigenfunctions of the kernel k. In view of the expansion theorem, the expansion coefficient alpha I can be easily written as alpha I is equal to integral from a to b of gx minus fx multiplied by fix dx. By combining these two equations, we get g of x minus f of x sum over I from 1 to infinity of alpha I fix is equal to simply the integral a to b of the kernel k multiplied by the function f of y integrated over dy. Hence, from 11.16 we get alpha I is equal to lambda times integral a to b dx into integral a to b dy of kxy fy fix, using the fact that fiy is equal to minus lambda I a to b of kyx fix dx is equal to minus lambda I integral a to b of kxy, because k, the kernel, is symmetric, fix. We get immediately alpha I is equal to minus lambda by lambda I integral a to b dy or fy fiy. Then using these equations, we get minus lambda by lambda I multiplied by the integral a to b of fy fiy is equal to integral from a to b of gx fix minus the integral a to b of fy into fiy. Hence, 1 minus lambda by lambda I multiplied by the integral from a to b of fy fiy dy is equal to the integral from a to b of gx fix dx. Hence, from 11.16, we get alpha I is equal to integral a to b of 1 minus lambda I divided by lambda I minus lambda into the function g of x into the function fix of dx, which can be written as integral a to b of minus lambda divided by lambda I minus lambda multiplied by the function g of x and fi of x dx. Hence, from 11.15, we get f of x is equal to g of x plus lambda times the sum over I from 1 to infinity of the integral a to b gy lambda I minus lambda fiy dy fix. The analysis presented above shows a possible singularity at lambda is equal to lambda I, as is clear from the final result shown in equation 11.24. The eigenvalues lambda I precisely are the values for which the homogeneous equation with gx equal to 0 has solutions. The right hand side of the equation 1124 thus diverges if lambda equals any of the lambda i's, unless for that value of I, the integral from a to b gy fiy dy itself is 0. The set of such results presented above can be summarized as follows. They are known as the Fredholm alternative. For a real symmetric kernel kxy, the homogeneous equation f of x is equal to minus lambda integral kxy fy dy has solutions only if lambda equals a set of real numbers. Lambda I0, 1, 2, etc. are called the eigenvalues. If the number of such eigenvalues and their corresponding eigenfunctions are finite, say n in number, the kernel is degenerate, and then it is expressible as the kernel kxy can be written as a sum over I from 1 to n of the product of two functions fi of x, fi of y divided by lambda I, where fix are the solutions of the homogeneous equation for lambda is equal to lambda I. The corresponding inhomogeneous equation is fx is equal to gx minus lambda integral a to b kxy fy dy. This inhomogeneous equation has solutions for lambda not equal to lambda I for any value of the given function g of x. So if lambda is not equal to lambda I, this inhomogeneous equation has solutions for any value of the given function g of x. If lambda is equal to lambda I, then inhomogeneous equation has a solution if only gx is orthogonal to fix. That is, integral gx fix dx is equal to 0. So, students, let us summarize what we have learned in this module. We learned that every continuous function px, which is an integral transform of another function hx by a symmetric kernel k of x and y, can be expanded in a series in the eigenfunctions of the symmetric kernel kxy, and this infinite series is uniformly convergent. This crucial theorem thus extends the results that we had for degenerate kernels and immediately leads to solution of the inhomogeneous Fredholm equation. For a real symmetric kernel K, the homogeneous equation f of x equal to minus lambda integral kxy fy dy has solution only if lambda equals a set of real numbers called the eigenvalues. If the number of such eigenvalues and their corresponding eigenfunctions are finite, then the kernel is said to be degenerate. The corresponding inhomogeneous equation minus lambda a to b kxy fy dy has solution for lambda not equal to lambda I for any value of the given function g of x. For lambda is equal to lambda I. So what we are trying to say is that this equation has solution for any given function gx provided lambda is not equal to lambda I. If lambda is equal to lambda I, solution exists only if gx is orthogonal to fix. Thank you.